It is the autumn of 1943, and somewhere over the grey waters of the North Sea, a modified de Havilland mosquito banks hard to port and descends through a layer of thin cloud. Inside its cramped fuselage, past the aluminium ribs and rattling instrument panels, something is alive. Something that should not, by any rational measure of military science, be part of a precision bombing system. 3 homing pigeons sit in a padded compartment behind the pilot's seat, their feathers ruffled by the vibration of twin Merlin engines, their small eyes bright and alert. They do not know they are part of a weapons program. They do not know that the fate of a reinforced concrete U-boat pen may depend entirely upon what they do next. This is not a story about eccentricity, though it will certainly seem like one. This is a story about a genuine engineering problem, one of the most intractable problems the British military faced during the Second World War, and the genuinely extraordinary, deeply serious attempt to solve it using the most improbable guidance system ever conceived. The project had a name. It was called Project Orcon, and what it attempted to do was turn a living bird into the world's first precision-guided missile. The pigeons were not passengers. They were the bomb. To understand why British scientists arrived at this conclusion, why men in laboratories at the National Research Development Corporation sat across tables from ornithologists and homing pigeon specialists and discussed with complete sincerity the aerodynamic tolerances of a bird's visual field, you must first understand the scale of the problem they were trying to solve. Because in 1943, despite every technological advance the war had produced, despite radar and proximity fuses and the remarkable navigational feats of Bomber Command, the British couldn't reliably hit a target the size of a football pitch from altitude. Not consistently, not when it mattered. The bomb had always been a blunt instrument. Drop it from high enough to survive the flak, and it scattered across hundreds of meters. Drop it from low enough to aim it properly, and the aircraft flew directly into whatever was shooting at it. The Germans knew this. They built accordingly. The reinforced concrete roofs of the Lorient and Brest submarine pens were, in some places, 7 meters thick, roughly the height of a double-decker bus, solid concrete capable of absorbing direct hits from standard British bombs without so much as cracking. And those pens were sheltering the very U-boats that were strangling Britain's Atlantic supply lines. The problem, to appreciate the desperation behind Project Orcon, you need to understand what precision bombing actually meant in practice during the early years of the war, and how catastrophically short of the ideal reality consistently fell. The Butt Report of August 1941 is one of the more sobering documents in British military history. Commissioned by Lord Cherwell, Churchill's scientific advisor, it involved a meticulous analysis of over 600 photographs taken by RAF bombers over Germany during night raids. The conclusion was devastating. Only 1 in 3 aircraft, claiming to have bombed their target, had actually placed their bombs within 5 miles of it. Over heavily defended cities, the figure dropped to 1 in 10. 1 in 10. The RAF was essentially paying an enormous blood price, crews, aircraft, fuel, manufacturing capacity, to scatter high explosives more or less randomly across the German countryside. By 1943, some of this had improved. The development of OBO, a radio navigation system that allowed Pathfinder aircraft to mark targets with colored flares, had significantly increased accuracy for following bombers. The introduction of H-2S, an early airborne radar system that could produce a rough ground map, gave navigators something concrete to work from. But these improvements, real as they were, remained statistical improvements. They raised the probability that bombs would fall closer to their target. They did not, and could not, guarantee a single bomb would strike a specific point. And specific points were exactly what the military needed to hit, not city centers, not railway marshalling yards stretched across a square kilometer. Specific reinforced structures. The submarine pens at Lorient, Saint-Nazaire, Brest, and La Pallice were engineering achievements in their own right. Enormous blast-resistant shelters that housed the very vessels conducting the Battle of the Atlantic. In 1942 alone, U-boats sank over 8 million tons of Allied shipping. The arithmetic was merciless. Britain depended upon roughly 1 million tons of imports each week simply to sustain its war effort. The submarines were winning. The RAF threw everything it had at the pens. In January and February 1943, Bomber Command launched a sustained campaign against Lorient that reduced the surrounding town to rubble and killed hundreds of French civilians. The pens themselves were barely scratched. American 8th Air Force, B-17, attacked in daylight at considerable cost in aircraft and crew, achieving similarly negligible results against the concrete structures. What the Allies needed was not more bombs. They needed to place a bomb exactly where they wanted it, from altitude, under fire, against a structure specifically engineered to survive everything they possessed. The Americans were working on television-guided glide bombs. The Germans had already deployed the Fritz X radio-guided bomb to lethal effect against HMS Warspite and the Italian battleship Roma. But both systems had fundamental weaknesses. They required a human operator in the launch aircraft to maintain line of sight with the bomb until impact, which was both dangerous and unreliable in poor visibility. They could be jammed. The Germans had begun deploying electronic countermeasures that could confuse radio guidance systems, causing bombs to veer wildly off course. What was needed was a guidance system that could not be jammed, that could not be deceived by static or interference, that operated entirely independently of any radio signal. Someone, and the records are not entirely clear on who first proposed this with serious intent, realized that a pigeon could not be jammed. The solution. The project that emerged from this realization was not, it must be emphasized, a joke. It was assigned to serious scientists at serious institutions and given genuine funding and genuine priority. The key figure in its development was the American behaviorist Burrhus Frederick Skinner. Yes, that B.F. Skinner, the father of operant conditioning, who had been developing the concept independently in the United States under a program funded by the National Defense Research Committee. The British version, Project Orcon, developed in parallel and in eventual coordination with Skinner's work, brought together ornithologists, aeronautical engineers, and psychologists in an effort that was either brilliantly unconventional or completely mad, depending on how you look at it. The mechanism was, in principle, elegant. A pigeon, it turns out, has remarkable visual acuity, considerably better than a human being's, and capable of detecting fine differences in pattern and shape at distance. More importantly for the project, pigeons can be trained, through Skinner's own methods of operant conditioning, to peck at a specific image, a shape, a pattern, a particular configuration, and to sustain that behavior reliably under stress, in noise, in vibration, in conditions that would reduce a human operator to uselessness. The system worked as follows. A nose cone was designed for a standard bomb casing, roughly 450 kilograms, approximately 1,000 pounds, of high explosive. Inside this nose cone, ahead of the main charge, sat a small padded compartment containing between 1 and 3 pigeons. Before each other, at the very front of the compartment, was a convex lens connected to a circular screen, roughly 15 centimeters in diameter, approximately the size of a dinner plate. As the bomb fell, the lens projected a live image of the ground below onto the screen, updated continuously as the target grew larger in the field of view. The pigeons had been trained over weeks of conditioning sessions to recognize a specific target from the air. They were shown aerial photographs of the target, a submarine pen, a power station, a ship, and rewarded with grain every time they pecked at the correct image on a training screen. By the time they entered the operational nose cone, they would peck automatically and persistently at their trained target image the moment it appeared on the screen before them. And here is the crucial part. The screen was connected to a control system. When a pigeon pecked at the center of the screen, nothing happened. The bomb continued on its trajectory. When it pecked off center, toward the left say, the bomb's small control fins adjusted accordingly, nudging the weapon back toward the target. The pigeon, in effect, was the guidance computer. Its beak was the joystick. Multiple pigeons were used to prevent individual error. If one bird lost confidence or was distracted or pecked erratically, the system took an average of all inputs. 3 birds working in consensus produced a guidance signal of remarkable consistency in laboratory conditions. Skinner reported that in tests, pigeon-guided missiles could be brought to within a meter or two of a target in controlled drops. Accuracy that no electronic system of the era could reliably match. The bomb casing itself was a modified general-purpose design, fitted with the bespoke nose cone assembly. The lens system and screen added roughly 12 kilograms to the overall weight. The control fins were pneumatically actuated, driven by compressed air from a small canister, and capable of adjusting the bomb's trajectory by up to 15 degrees in any direction. The total apparatus occupied a cylindrical space approximately 30 centimeters in diameter and 45 centimeters in length, roughly the dimensions of a large kitchen bin, machined at several facilities, including workshops in the English Midlands. The components were assembled and tested at a facility whose exact location remains somewhat obscured in the available records, a deliberate vagueness that speaks to how seriously the project was taken from a security perspective. Operational use. Here the historical record becomes, of necessity, rather more sparse. Project Orcon never reached full operational deployment. The program was ultimately cancelled in the United States in 1944 and in Britain around the same period, before any pigeon-guided bomb was dropped in anger over an actual enemy target. The reasons for cancellation are worth examining because they are instructive and because they tell us something important about the gap between laboratory success and operational reality. In controlled test drops over designated ranges, the system performed remarkably well. Pigeons trained on specific target photographs consistently guided test bombs to within acceptable accuracy margins. Several accounts from participants in the program describe watching the bomb's trajectory visibly correct itself mid-fall, the fins making small adjustments as the birds pecked at the image below them, the weapon homing toward the painted target on the range with an eeriness that observers found difficult to articulate. The problems emerged when the program attempted to bridge from the controlled environment to operational conditions. Training a pigeon to recognize an aerial photograph of a submarine pen was relatively straightforward. Training it to recognize that same target as seen through a lens, at altitude, in varying light conditions, from an approach angle that might differ by 30 degrees from the training image, was considerably harder. Pigeons trained on summer reconnaissance photographs performed poorly against winter images of the same target. Those trained on photographs taken from one altitude became confused when the bomb was released from a different height. If you are finding this interesting, a quick subscribe helps more than you know. There was also the question of recovery. The pigeons, obviously, did not survive the impact of the bomb they guided. This troubled some participants in the program less than others, but it raised a logistical question about training pipelines and whether the investment in conditioning each bird, a process taking several weeks, was sustainable at operational scale. Comparative analysis. It is worth pausing to compare Project Orcon with what the Germans and Americans were simultaneously attempting in the field of precision guidance, because the comparison illuminates both how serious the problem was and how different the approaches to solving it could be. The German Fritz X was the most operationally successful precision-guided weapon of the war by the time Project Orcon was being developed. A radio-controlled, armor-piercing bomb weighing approximately 1,570 kilograms, 3,460 pounds, more than 3 times the weight of the pigeon-guided weapon. It was steered by a bombardier in the launch aircraft, using a joystick and a radio transmitter. On September 9, 1943, a single Fritz X sank the Italian battleship Roma in less than 10 minutes after she had surrendered to the Allies, killing over 1,300 men. It was a remarkable demonstration of what precision guidance could achieve. But the Fritz X had to be deployed from high altitude to avoid flak, and it required the launch aircraft to maintain a straight, level course for the duration of the bomb's fall, sometimes as long as 45 seconds. This made both the aircraft and the bomb vulnerable. Allied forces quickly developed jamming equipment that could disrupt the Fritz X's radio guidance, and instances occurred where jammed bombs veered wildly, sometimes back toward the launch aircraft. The system was not robust against electronic countermeasures. The American Pelican, a television-guided glide bomb developed in parallel, suffered from similar vulnerabilities and the additional problem that its television transmission could be jammed or degraded by weather and atmospheric interference. Developed at a cost vastly exceeding Project Orcon's modest budget, it never reached operational effectiveness. What Orcon offered, theoretically, was immunity from all of this. No radio signal, no television transmission, no electronic signature whatsoever. Just 3 birds, a lens, and a screen. The guidance system was entirely self-contained, entirely passive, and entirely unjammable. In terms of its fundamental concept, it was arguably ahead of everything else being developed at the time. A biological seeker head that processed visual information with a sophistication no electronic component of the era could replicate. Modern precision-guided munitions use laser designation and GPS, systems whose underlying principle of maintaining a sensor locked onto a target is conceptually identical to what the pigeons were doing. Project Orcon was merely using the wrong substrate. Impact and legacy. The honest assessment of Project Orcon's historical impact is a complicated one, because a weapons system that never fires in anger leaves its legacy in the realm of the hypothetical. Had Orcon reached operational deployment, and the engineering problems, while real, were not considered insurmountable by the scientists involved, it might have changed the calculus of the submarine war significantly. The U-boat pens remained functional and largely intact until they were overrun by Allied ground forces in 1944 and 1945, not destroyed from the air. The Atlantic campaign cost the Allies an estimated 3,500 merchant ships and 175 warships over the course of the war. Whether Pigeon-guided bombs could have shortened that campaign by months or even weeks is impossible to say. What the project undeniably demonstrated was the principle that biological systems could function as guidance computers, and that the key to precision attack lay not in brute force, but in the ability to maintain continuous visual lock on a target throughout a weapon's flight. This is precisely the principle underlying every laser-guided and imaging infrared guided weapon in use today. The Paveway series of laser-guided bombs, introduced by the Americans in Vietnam and still in service today, functions on an identical conceptual basis. A seeker in the nose of the weapon tracks a laser spot illuminating the target and adjusts the weapon's fins to keep it aimed at that spot. The pigeon was the seeker. The image on the screen was the laser spot. Surviving documentation on Project Orcon is held partly in British National Archives and partly in American records relating to Skinner's parallel program. Some material remains classified or has not been fully processed for public access. The pigeons themselves, obviously, left no archives. What survives of the nose cone apparatus, if indeed any prototype components survived the war and its attendant destruction, has not been identified in any public museum collection, though researchers continue to look. Closing, return for a moment to that mosquito over the North Sea in the autumn of 1943. The birds in their padded compartment, the grey water below, the whole elaborate, improbable, entirely serious apparatus of the thing. Consider what had been attempted. In a decade that produced radar, jet aircraft, penicillin, and the first steps toward nuclear fission, a group of scientists and engineers had looked at the problem of precision guidance and concluded that the most elegant solution available to them was a living creature with a brain the size of a walnut and an evolutionary heritage stretching back 65 million years. They had not done this as a joke or as an act of desperation, though desperation certainly played its part. They had done it because the mathematics of the situation demanded it, because nothing electronic could do what a trained pigeon's visual cortex could do, because the gap between what technology offered and what the war required was wide enough that biology had to fill it. The project did not succeed in the sense of firing in anger. It did not save the merchant ships already lost or shorten the U-boat campaign by a single day. The submarine pens at Lorient still stand, enormous and virtually indestructible, tourist attractions now, their concrete roofs unbroken by anything the Allied air forces threw at them. They are a testament to the limits of what bombing could achieve in the 1940s, and to the scale of the problem that Project Orcon was trying to solve. But consider what it demonstrated. Consider that a team of scientists in the middle of the most destructive war in human history found time to train pigeons to steer bombs, built working prototypes, conducted successful tests, and came closer than almost anyone remembers to deploying the concept operationally. Consider that the fundamental principle they were working from, a visual seeker in the nose of a weapon, tracking and correcting continuously, became the founding principle of every precision-guided munition developed in the subsequent 80 years. They were right. They were simply using the wrong technology. The Pigeons could not be jammed. They could not be deceived by electronic countermeasures. They processed visual information with a speed and accuracy that no vacuum tube computer of the era could approach. What they could not do was be trained quickly enough, reliably enough, for all the targets that a war requires you to hit. What they could not do was survive the digitization of warfare that was still decades away. The laser came, the GPS came, the imaging infrared seeker came, and every one of them does, in silicon and photons, precisely what 3 homing pigeons were being asked to do in a padded compartment behind the pilot's seat of a de Havilland Mosquito over the grey waters of the North Sea. The Pigeons were right. They were just too early.